And there we go. Okay, so today we're going to basically pick up where we left off last time, which is the recurrence relations. However, we've gotten through most of it now at this point. I believe the write-up is 30% of the extra credit points, so you still get some of the extra credit points. That's quite a bit. So yeah, always do write-ups for every assignment. But yeah, so basically, we did the longest example last time. Very quickly to review that example, since it's been a long weekend. We started out with this recurrence relation right here. And so rather than trying to solve it from going from 0 to n, we said let's solve it from n to 0. And so n here is not n, it's actually, well, it is n, but like you see that it's increasing in half. So it goes to half, then a fourth, then an eighth, and so on. That's not something that we saw immediately possible. I mean, we might have, but you didn't have to. But we did eventually see it as we ran through the different iterations of this. What we did is we basically plugged in the next step in the algorithm, so the next sort of recursive call. So we plugged in the n divided by 2 where n was. And by doing that, let me highlight so you know what I'm pointing at. So there we go. So here, this is what we did. We plugged that in by solving it, by just putting a divided by 2 or wherever you saw the n. And then we put that in here, and we simplified it, so we got this. And so now we got n divided by 4. So we did the same thing by plugging it in, taking that, and putting it there. And so we found out that common pattern that was that every step that we went, step 1, step 2, step 3, where each step is an I, it's basically 2 to the I times this recursive function n divided by 2 to the I plus I times 4n, right? And so if we're in the 5th step of this, I is equal to 5. And so because we know that the final step is the one where this internal recursive call is just 1, so this n divided by 2 to the I is 1, then we just make that a simple, like, you know, algebraic thing where n divided by 2 is equal to I. Like, what value of I is going to make that equal to 1? And then we just use our logs for that, and it's just basically going to be log n. So whenever I is equal to log n, then this should be equal to 1. And so we just plug that in. We plug in log n for I into that equation here, and so we end up with this, which is 2 to the log n times t n divided by 2 to the log n. Again, the reason we're doing this is because we know that this will simplify to 1. And we know what this is because this is the base case. It's equal to 2 or whatever I said at the top. 2 or 4, I can't remember. 4, yeah, 4. And so we, you know, that leaves us with this line here. So we know this is 4, so we can just change that to 4 as we do here, right there. But the rest of the stuff, 2 to the log n and then the log n times 4n over there, we still got to solve. But it's not as bad now because, again, the end game here is we want to solve any t parts. Anything that says t with parentheses, which is a recursive call, we want to get rid of those. That's how we know we're done. And so basically, by doing that, you know, by doing this t to the 1 substitution, then we just throw away that recursive because there's no more recursive. We're at that base case per se. And so we only have the t event here, which is what everything is equal to. I just don't write it in. But from here, we can just basically simplify this. At this point, we're done. We're just making it look prettier because 2 to the log n is kind of a weird number to understand. But we can use this property that we talked about one of our logarithms, which is where you can just flip these numbers around. And then I think I explained to all of these and why they work. But yeah, you just do that with the 2 to the log n, and it just becomes n to the log 2, which is log 2 is just 1, so it becomes literally just n. So really, this 2 to the log n is just a fancy way of writing n. So when you do that, then you just get this now. This looks much prettier now. At this point, I just, you know, multiply the 4 in the n and put it together like this. So this is one way of leaving it, or you could leave it like this. These two are the same. I'd say they're both simplified enough. For big O's terms, I prefer the top one because I erased it. Thanks. I prefer the top one because it looks a little bit nicer and it's easy to understand that this is kind of insignificant because this term is bigger. You know, this is literally just like this, but slightly like this is the same as this, but this has a log n to it, so it's always going to be bigger. So in terms of big O, we don't care about this term. We really care about the biggest term. In terms of theta, yes, we put the whole thing, which is why we put that. But if we want to talk about big O, we say, well, you know, this term is whatever. This term, this number is or whatever. What we really care about is this n log n component. The rest of the stuff is just constants. Big deal. For constant purposes, this is actually a nice way of seeing that, because this 4 is just a constant. Once you throw that away, you got your n log n plus n, and you can see that this plus n isn't really going to do much when you have an n log n, right? It's like if you have x times x to the 10 power plus x. Well, the x to the 10 power is where all the like number stuff is going to come in. The plus x is going to be like an afterthought. So that's why you throw it away. But you formally say that by saying it is an element of this category given this constant, given this minimum n. Okay? Which one? Which pi symbol? This one? Well, it's theta. Theta. So the circle with the dash is a theta. So make sure that y'all remember that. Theta, omega, and big O. Okay? So yeah, that's pretty much what we spent an hour last class doing, almost. So yeah. Need some water. Okay, so that's what we did last time, and so today I wanted to show you a different example. This is the one where I just kind of go really quickly over because it's kind of like the same thing but in a different way of doing it, and there's not point in me showing it to you because you're going to go over a lot of this in algorithms class. So I'm just first going to copy and paste. You know, if we were in class, I'd project this on the board, but here I can just copy and paste it from an image, hopefully. We'll see if that works. And then I just talk about that example and we can move on. Because what I want to show you today is the Master Theorem, so that we can just move on from this and start talking about other stuff like sorting and linked lists and whatnot. Okay? So really this is going to be the last day that we talk about recurrence relations. But you'll see them all semester long because, you know, when you do your write-ups, one of the things that you can do is do the recurrence relation, show your work, and then say, okay, this is the time complexity of this recursive code that I wrote. It's inefficient and sucks, but you know, I wrote it. Or it's amazing and it's great. Here's why. Okay? So really, I should really put here also the Master Theorem. And then let's all smile for the thumbnail. Okay. All right. So, ooh, that looks kind of blurry. Actually, it looks better for you than it does for me here. But okay. If not, I can try to take another picture of it. But basically, if I do recursion on the big number, can that cause a Stack Overflow? Yep. Recursion is great. You know, it's ironic because a lot of people think of recursion like it sucks and why do we want to do it? But it actually turns out that the reason you use recursion is because it makes some algorithms easier to represent and solve. That you're not there yet, but I think by the end of this class you will be there. When you see things like quicksort. Recursive quicksort is like 1,000,000 times easier than like lamp sort, which is essentially iterative quicksort. So you actually use recursion to make problems easier to solve, such as traversals and trees. That would be a really good example of recursion. But the problem is recursion is not efficient at all, and it sucks actually. We don't actually like recursion because you can't really parallelize some of those things, and it's a pain. And so, ironically enough, we use it because it's easier to solve problems recursively. But in efficiency terms, you actually want to avoid it. And an obvious example of that is when you have a lot of recursive calls because they use up a lot of memory. So, yep. Should I use reference variables for recursive functions? So the traditional way of doing recursion is to pass by value and then return the updated values. But using by reference is okay. You just, you know, like, because that was the thing with the questions on Discord over the weekend, if you could use like statics, you're really just kind of getting around the recursion by like keeping states outside of the functions. But to truly understand recursion and what you'd use it is because you want to keep all the states within that recursive call. It's that sort of functional programming mentality, but you'll get it with time. So, yeah. Let me just take out this here. Okay, this might be clear. I don't like how that looks blurry. So let me try again with the photo. See if I can get it a little better. Okay, so stand by. I will take a picture of a picture. I think. Okay, so let me. I don't want weird things to happen. So let me switch over to that image and then open my camera app. I don't want it to like crash trying to stream the camera or something. I don't really use this iPad for anything other than teaching, so I don't even know what a camera app is. Okay, here we go. So, alright. Oh yeah, this looks so much nicer. I don't know why that one came out so bad. Let me just get it. Okay, there we go. So, let's go back to this. Go back to the chat. And then let us try to re-import this. Actually, hold on. I don't want weird. I don't use this, but what if like there's like a weird picture in here? So I don't want weird things to happen. Paste image. No. Add camera. No, not camera. Cancel. Photo library. All photos. There's nothing. Okay. Very cool. So I have to use the document scanner. Okay, let me just try to take the photo within the Notability app, I guess. That one looks not as great, but okay. All right, use photo. Okay, that looks more readable, so we'll go with this. Okay, all right. So yeah, it looks better. Like before it was blurry. So okay, it's kind of crooked, but you know I don't want to spend too long trying to get a picture of this. So this is the one. I don't know if it'll look better with the webcam. Probably not. Yeah, no. So okay. All right. So yeah, okay. And I can zoom in more. So I'll zoom in as I go over. So basically, here we have the exact same problem as last time. Like the same recursive recurrence relation. So that 2tn divided by 2 plus n, okay? Except the we're gonna do basically a different approach of solving this. And this is actually more of like I think the one that Dr. Iwali likes to do in algorithm analysis class. If you take it with him. So, you know, like I said, I'm gonna go really briefly over this because it's a good introduction, but he'll go over in detail and make you do homework and everything on this. So it's called the tree method. And so you basically start out the same way that you start out with the other one, which is you start from n trying to get to 0. And you have the same concept that you're still trying to come up with this common like function, this 2 to the I thing that we did. So you know, the one that I did over here. So let me scroll up to make sure we're on the same page. You're still trying to come up with this one. This is like the pattern essentially, right? That's what you're trying to do. That's the end game. But the way you get to that is a little different. It's more graphical. So you start out by saying, okay, well, you know, we have our Tn, and that kind of represents when I is equal to 0, which is the starting point. And so in that case, we know that we have just this 4n situation, okay? We have this just 4n. And we know that the next time that we do this, and how we get the 4n is because it's up here. Let me use the laser pointer. So this here 4n, we put that here because we know that's there, right? Because that's the only part, like remember, this t to the n part, that just means there's no more recursive calls. But the only thing that's actually like adding time per se to our recursion is this. So if you have a recurrence relation that says t of n is equal to t something 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 parentheses and then plus and then something else, that something else, as long as there's no t's in there, that's actually how long something takes. So when you see something like t of n is equal to t of n divided by 2 plus 1, that plus 1 is actually the time it takes to run that recursive like call. That one recursive call before it calls another one, okay? So in this case, it's saying it takes 4n, okay? So the t of n stuff is irrelevant. That's just like other numbers you plug in, right? And so that's why we're saying here that in this step, it takes 4n time. So now the next step, when we do n divided by 2, we see 2 of these, the 2 4n's. That's because we have, you can think of like the old one and the new one, but we haven't divided by 2 because it's divided by 2. And so from there, you get 4 out of that because you plug it in again. And so you get 4n, 4n, 4n. And then here you get divided by 4s instead of divided by 2s. So you're essentially doing the same thing that we did last time, which is just plugging it in and trying to figure out how many of those you get. So if I go back up to this thing, you're essentially plugging it in like we did here, and you're getting this 4n, and then when you plug it in again, you see that you get 2 4n's, and if you do it again, you see that you get 3 4n's, and so on. So you sort of start seeing that, but doing it sort of visually here, okay? And you see that every time you do this, that there's always going to be a 4n that's added in. And so that's when you pick up the pattern, you say, well, okay, it's just, this is going to take as long as the i's are, times 4n, which is true. Every time we go one step, it adds 4n to our time. That's literally all this is doing, is adding 4n, 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 and so on. And so you sort of come up with that general solution again of 2 to the I by saying, whenever we have n divided by 2 to the I, then this becomes 4n divided by 2 to the I. And then over here, this 2 is coming from this 2 right here. So you just add this 2, which again keeps getting a power, so it becomes 2 to the I. So really, here, you're getting the exact same thing that we got, except this is more of a visual way. Mine was more of like hard, math, plugging and stuff in. But ultimately, you end up with the same thing. Now, this looks a little fancy, but really, this is just another way of writing that 2 to the I function. We're saying that the sum of all of the 4n's from I to 0 all the way to log 2n, because log 2n is when, again, this becomes I, so this n divided by 2i, we want this to become, the base case. So we want it to become I. So it's got to be the summation of that. So that's why you see the summation symbol. Again, it's a little fancy, but if we're doing the exact same thing as last time. That's just going to be equal, to 4 times, again, that summation times 1. If you plug that in, it ends up being a bunch of 4n's added together, like we saw before. And on this side, it ends up being, again, 4n's basically added together. Each time you add one of them, all the way to log 2n. Ultimately, when you add that together, you would actually end up with the same result, which is this. But this requires you to understand how limits and calculus work a little bit to understand that this becomes that. But, you're more than welcome to see this. And there's, you just Google like tree method with recurrence relations and figure and see examples. But that's all I'll say about that. I just want to make you aware that it exists again. Dr. Gawale will spend like class periods actually going on this. So, yep, that's really all. That's why I don't want to spend time drawing this and everything when I can just show that. But yep, that is that. Okay. Moving on to the next one is the interesting stuff, the Master Theorem. Okay. So for the Master Theorem, let me start out by linking you to Wikipedia on the Master Theorem, since we don't really have a lot of time to talk about it. Again, Master Theorem is something that is really part of this course. It's part of algorithm analysis, but I like to show it because since people struggle so much with recurrence relations, and the Master Theorem is like the shortcut to them, might as well show you the shortcut now so you don't struggle so badly. Again, I'm just going to take a picture that I already have of that. I think this one actually came out a little better. We'll see about that. Very cool. Okay, let me try something else here. Copy. Okay. Yeah, this worked out. Okay, so this one's actually nice. So this is the Master Theorem, okay? The Master Theorem is like the cheat code to solving some of these recurrence relations because it gives you the answer. Like it just gives you the answer. It's cool. It's just like it's cool like that. It doesn't always work. Like nothing in math always works. There's always the edge cases, but it'll work for the majority of the problems you get in school for sure. And the majority of the simple problems that you'll see in life, you get something that will obviously be the special case that will not work, and then you'll be like, dang it. But most of the time, it'll work. Okay. All right. So, okay. I got more notes than that to give you here, but okay. So this one's this picture. So actually, it's cut off. Oh, it's because it's zoomed in. Okay. So you'll have the entire thing there. The Master Theorem is very complicated. I am really going to be hand waving a lot of things and just showing you like how to use it without explaining you the theory as to the why it works and whatnot, and just run you through some examples and then move on, okay? And basically, we'll try to do all of the examples I have, but if we run out of time in class, that's okay. Like really, you know, I just want to show you the basics so you can take advantage. And this will help you with your assignments too, to do the recurrence relations, because I really doubt, unless you're doing some really nasty code, that you won't be able to use this. Okay? So, let us kind of start out by explaining to you, again, how this is represented, this recurrence relation, okay? So, when you read something that says like T of n is equal to something, and then you get that T of n on the other side, so like here we have, you know, let me make this a little, there we go. You know, we have T of n is equal to A times T of n divided by B. This is some constant, and in this case was 2 before, plus something else where it's actually the time, like that 4n or whatever. When you're reading this, the way you properly say this is the runtime of an algorithm on an input of size n, which is this one, is usually denoted as T of n, and can be expressed by this recurrence relation, where f of n is the time to create the solved problem. So f of n in this case is where the theta of n is. So if I put something like this in here, so T of n is equal to A. Don't worry what that is, it's just some number. Oops, don't want to put a number there, let's put another letter. Plus f of n, okay? So, when I'm talking about an algorithm, and this is what you'll be doing again in your write-ups, so the runtime of an algorithm of input size n, so that's the amount of input. So think about sorting, okay? Your input is the number of numbers, or the number of items that you're trying to sort. So if you're trying to sort 100 numbers, n is equal to 100, right? So size n, okay? The runtime of an algorithm of input size n is usually denoted as T of n, okay? And is expressed by the following recurrence relation. This f of n over here is the time. So f of n is the time to create the subproblems. What do I mean by subproblems? Again, when you're trying to solve a large problem, you usually use recursion to sort of approach it by solving smaller pieces of it or a subset of it, okay? So for example, if you're trying to sort a bunch of numbers recursively with quicksort, what you're essentially doing is you're partitioning things and working on a tiny piece first, okay? So the basic idea here is that it's kind of like a little bit of divide and conquer approach that you learn in 135, you know, where you take a problem and split it into smaller problems and so on. But ultimately, what you're doing is you are breaking a problem into smaller problems that are easier to solve until you get into really, really tiny ones that you just solve and then build it back together, okay? And so that's the idea, that this f of n is a time to create those subproblems. So it takes time to actually break the problem apart and then to be able to combine the results of the subproblems back into the big problem, right? Because I mean, yes, you solve the small problems, but then you got to actually build it back together to solve the major problem. So like if you're like, okay, how do I cook an egg? Well, first you got to get the egg, and then you got to go find a pan, and then you actually got to cook the egg, right? So you break it into all three subproblems, but then you got to actually put them together once you solve them, at the time together it took to solve all of them, and then you say, okay, it takes me this long to cook an egg, okay? After combining everything from driving to the grocery store to get the egg, to getting a pan, and to actually cooking the egg, okay? So it's not just breaking it down, but also putting it back together. As for the question in the book, I have no clue. I list that book because it's a good reference, but I kind of just go on my own sort of pattern. The best way to figure out my pattern is look on Canvas. That's sort of like the schedule of the modules is how I go. But I don't know how the book is structured. I haven't looked at it in a long time. But I do know that they have a section on recurrence relations in Master Theorem, and they have some good examples. I just don't know which chapter that is. But I do think I jump around with the recurrence relations. I don't think it's like in the beginning of the book. So to answer your question, So anyways, going back to this, let me just write down what I said. Okay, so ultimately f of n is going to denote the amount of time. And remember, time is relative in the sense that, like, you know, we can say seconds, but really we're talking about operations. It's because computers run at different speeds, you know. But, you know, just to make it easy to kind of get it into our heads, I'll say seconds for now. Okay? So f of n is going to denote whatever has been built up to that point. It could be all the way to the bottom of that little tree of work to do, or it could be at the top, you know, but whatever's left is whatever the t of n is there. So if you think about it this way, f of n is how far we've solved the problem, and then t of n is what we have left to solve. If we're at the base case, then there's nothing on the t of n side. It's just an f of n part, and it's t of 1 or something. If we're at the top, then it's something like t of n plus f of n, and f of n has like a lot of work to do, okay? So once you kind of understand that that's how this recurrence relation stuff is set up, then we can understand why the Master Theorem works the way it does. So the Master Theorem, what it is sort of like this little template of a function that has t of n is equal to at n divided by a b plus theta of nd, okay? Now in here, this theta of nd is going to be the f of n I'm talking about. And then the rest is just going to be what it is. The a and the b are probably going to be some sort of constant, some number. Well, they have to be constant, but it can be any constant. So it could be a 1, a 2, a 50, a 40. It just cannot have something related to an n associated to it, okay? And there's also a couple of other limitations with the Master Theorem, which kind of show you that it doesn't always work. And that is, for example, that the value that fits into a has to be a positive number, greater than 0. The value that fits into b, well, I hope that's obvious why that shouldn't be 0, because you can't divide a number by 0, right? However, you could divide by a negative number, but in this case, it does not like negative numbers there. It has to be a positive number greater than 1, but not equal to 1, greater than 1, okay? So if you just have t of n, the Master Theorem doesn't actually really like that here. So, yeah, you can't really use that in that case. And finally, you can see that this f of n thing is structured in the way that you have n to a power of d, and that power can be anywhere from 0 to or more. And remember that if it was power of 1, there's just be an n there. But if it's a power of 0, it just gets rid completely of the n. So you could potentially say something like plus 1, and that would be okay. It's just that n is equal, d is equal to 0. Okay? So what you do is you take your recurrence relation and you format it so that it fits in that order. And when you do that, you're going to end up with 3 possible scenarios, okay? And depending on those 3 possible scenarios, you know how to solve it already, okay? And the scenarios are going to depend on what the value of d is, okay? So if your d is equal to 1, 2, 3, or whatever, you know, what you need to do is you need to figure out what the logarithm of base b, or so log of b with a is, and then compare that to the value of d, okay? So where does v and a come from? Again, you take them out from the top, so it's like you get the a from here, and then you get the b from down there. And don't worry, we'll do examples in a minute. And then you take those things, and then you run the log b of a part, okay? So here we're no longer doing potentially logarithm with 2. We're potentially doing it with a completely different base here, okay? We could be doing it with any number that is under the a. Usually it's going to be, or sorry, under the b. Usually it's going to be like a 2 or something, but it could be a different number, technically, okay? So you take that, and this is a very simple thing to calculate. Obviously, this might not be an exact number because, you know, you might get something like log 2,3, and that's, you know, that's like 1 point something. It's like 1.5 or whatever. But ultimately, you know, you pop out a calculator or run like a Python terminal and just plug it in and see what happens. And then compare that value with the value on d, okay? And you're going to have either a scenario where d is greater than this computation, where they're equal, or where they're less than, okay? They're called those case 1, 2, and 3. And once you do that, you're done. Well, you're like 99% done. The rest is that your solution is literally going to be right here, depending on those scenarios. So if d is greater than this value here, then your solution is literally going to be theta of n to the d power, okay? So if d happen to be 2, then your solution is n squared, done. If these 2 values happen to be the same, then your solution is going to be n to whatever the d value is, log n. So if d is equal to 1 and this happened to be 1, so this was like log 2, so this is 1 equal to 1, this would just be n log n, okay? And finally, the more kind of fancy one is this one, where if d is less than whatever this value is, then this becomes n to the log ba. Again, you know what these values are, b of a, so then you can actually compute whatever this number is, which might be like a 2, a 3, or whatever. But it could also be like an actual, fraction or something. And you could leave it like that with a log thing, but maybe it's kind of hard to read that sometimes. Okay, that's it. That is how the master theorem works. As you can see, there isn't like the hardest part here, I guess, is trying to figure out what this log is if you don't have a calculator and you need to have it like if you and this number was close enough that you're like not sure and you're like it's like 2.5 versus 2.4 and you're like, oh snap, is it 2.5, 2.4? But other than that, like, it's pretty easy. You get your solution right away. Like, it's nice. In fact, we're gonna do this with some examples. We'll do it with the exact same number, the same one that we spent an hour on last class. We're gonna do in like 30 seconds. Okay? So 30 seconds, 1 hour. Think about it when you're taking an exam. Which one would which one do you take? Okay, we have a question. Is it possible to have an if d is greater than or equal to? No, so you have to stick with the three cases as they are. Either equal, greater than, or less than. So if you have a scenario where your recurrence relation does not fit into this sort of template, then you're out of luck and you have to go the hardcore way and spend an hour. Okay? There's more to the master theorem than this. Again, check out, did I link you? I don't know if I posted. I'll post it again. But that's the link to the Wikipedia where you can read more about it. There's actually a couple of more cases when you talk about K and whatnot. So this is like the simplest part of the master theorem. But there's a couple of other cases that are more fancy, which I just don't have time to cover. But it's nice because again, it saves you lots of time. So if anything, you want to learn that so you can detect it when you can use it and then save yourself an hour. Okay, so I have a couple of examples here, but really I'd like to start with the one that we did last class because I think that one will show you the power of it more than anything. So yeah, let's just do the one I started. Let's just start with the one. So let's just copy paste it. This one. Where does it look kind of nice? Must have like a clean copy of it somewhere. Here we go. Wait, no, that's way too old. Okay, we'll just copy that one and clean it up. Copy. Very random, but I was watching Gordon Ramsay make a burger, and I'm on a diet, and now I can't just stop thinking about it. It's very depressing. Okay, so here we go. So for the assignment 2 upload, do we add those n values to the table, PDF, write-up, or into their own file? So the assignment 2 is special that the write-up is the solution that you're working on because you put your table and whatnot. So just do your table and then do your recurrences, and that's kind of your write-up as well. Okay? There's no, I guess there's coding, I guess, because you got to plug in the code and do the recursion. But I think I'm not sure if that's what you're saying. But I see what you're saying. Like, don't just make the TA like have to read less stuff. So like just copy and paste the table into its own document, because it'll be easier. Because if the TA has to scroll through the assignment entirely, it's a lot of pages. Or if you just put the tables, it'll be easier for him. Either way, it's okay, but I think that will make his life easier. Are arbitrary numbers present for A, B, and D? Well, no, that's the point. You take the numbers that you're given. So like that's what I'm going to show you right now. Okay? So yeah, you'll see. So look, this is what we got right now. This is the same problem that we worked on for an hour last class, okay? So what we're going to do is we're going to take, I'm going to write it here so that I can digitalize it, per se. Here, there. T of n is equal to AT n divided by v plus theta and d, okay? So I'm going to take that and I'm going to copy it. I don't think I copied it. Hold on, try it again. Also, while I'm at it, let me fix it because it's not straight and it's crooked. Okay. All right. So we have this and we have that. And let me paste it down here since we're going to use it later again. What we want to do is we want to figure out what A is equal to, B is equal to, and D is equal to. That's step one, okay? So look at both of these, and like it should be obvious that, you know, things match, right? So let's color code it. So this here matches that. So that's probably going to be our A. This here matches that. It's probably going to be our B. And the D is a little weird. Green. But this foreign is actually this right here. Okay? That's it. That's all there's to it. Although, actually, well, it's a little misleading because what we're trying to figure out is the D. So really, the D is like whatever would be here. Okay? Which there's nothing. Very well, there technically is, right? Because if you all remember, if I have some math formula, so like W, X, Y, Z or whatever, Z, Y, whatever, blah, 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 whatever this is, doesn't matter what this is. You know, I can convert that to have an exponent by just putting a 1, right? So if I have n times 45, that is the same thing as saying 45 n to the first, right? That's it. And if I have something like 48, that's the same thing as saying 48 n to the 0, right? So these things are the same. So let me use equal signs there, right? So really, you know, make sure you remember like that sort of basic math stuff, okay? Let's just put that down here as an example. Okay, so yeah, so let's just put in the numbers in. Well, the A is obvious, hopefully, as to where that came from. So we're going to put a 2 there. And same with B, that's the purple one. For the green one, like I said, it's a little trickier, but it's a 1 because, you know, there's no exponent there because it's just a 1, okay? But yeah, that's all there's to it. We got 2, 2, and 1, okay? All right, step 2 is to compute that log BA thing. So we need to compute what the log BA is equal to, okay? So step 1, step 2, okay? So what is that equal to? All right, well, let's just plug. We already know what A and B are. So let's just plug it in. I mean, this one's easy, right? It's just 2, 2, which is just equal to 1. All right, so that takes care of that. So now we have 1. All right, now we're up to the final step, which is to figure out which of these 3 cases that is. Let me attempt to do a highly advanced copying and pasting here, which I've already screwed up. All right, maybe this will work, maybe not. Try it again. This is because I'm lazy and I don't want to rewrite that. But hey, it worked. I mean, after all, we're all programmers. We're here because we're lazy. We don't want to have to do things. We want computers to do them for us, right? So yeah, okay. So we got the 3 rules, right? And so in our case, D was equal to 1, and the log BA was equal, I think, also to 1, right? Yeah. So which of these 3 cases is that? Well, I hope I don't have to tell you, but you tell me. Which of the 3 cases is it? Case 1 at the top, the middle one, or the bottom one? 1, 2, or 3? Insert like the Jeopardy music in here. Middle. Yes, that is right. Very good. Well done. So this is indeed going to be the middle case, because they're equal, right? 1 is equal to 1. So what's my answer then? My answer is right here. It's going to literally be theta is equal to n to the d log n. And what is d equal to? Well, d is equal to 1, so I just plug in a 1 right there. So this just becomes a 1. So again, just throw it away, because who, you know, do we ever write to the powers of 1 when we're doing things? We don't. So we just say n log n. And if we scroll up here, that's what we have. Okay? There's a catch though. There's a little asterisk, you know. It's like read the terms and conditions kind of thing. Because we actually got big O's, like the simplification one. However, as we did by hand, the real answer is 4n plus 4n log n, right? But when we simplify it, so that's the terms and conditions, you know, that's where they get you kind of thing. The Master Theorem is going to give you that simplified solution of the n log n. It's not going to give you that 4n plus 4n log n thing that we had. So if you want the exact solution, you got to go the hard math way. There's no way around that. However, if you just want to get the big O, the quick one, which is really the one you care about, like 99.9% of the time, you use the Master Theorem. So, obviously, because I was talking about it in more than 30 seconds, but even so, 1 hour, 1 minute. You choose when you're taking the test, at least. Okay. Unless, of course, I ask you for the exact answer, in which case you're screwed. So, yeah. Okay. So I hope you know. I hope it paid off the whole wait and tell kind of to show you the thing, right? Can you zoom in, zoom out to see all the steps real quick? I can try, but it's kind of, you know, I mean, we're gonna do more examples like that, maybe. Okay. If not, again, on the YouTube video, you can probably screen cap stuff, you know, right there, and then there, and then there, and then there. Okay? So yeah, you can just screen cap it also from YouTube or Twitch. You can do you can clip it, but I don't know, that really works. You know, I discovered the clip it thing at some point in the middle of the semester, and it was all like memes that I was saying or something. I was like, oh wow, okay, very cool. Yeah. But, okay, so, yeah, you know, I don't know why I didn't do this as an example here, but maybe it's just because I always just do it intuitively, so I don't need to write that example down. But, you know, it's the best one because you can really see the difference in time. So, hopefully, you know, I convince you to actually embrace the Master Theorem and not just kind of, you know, forget about it kind of thing, okay? Here, it requires a little bit of memorization. I mean, actually, not really, because, you know, as long as you have, like, what I have, which is that little kind of like cheat sheet, which is this is what you really want. This is what, you know, this is what you really want to screenshot of, like this one, because this has everything in one page. So, like, you know, back in the day when they would say you can use a note card on the test, like, this is what I would put in that note card kind of thing. Like this stuff right here, because this is, you know, you have to memorize this or you have to write it down. So this is what you want to always have. But with time, you know, yeah, at least you want to be able to detect whether something is Master Theoremable. Okay? So you'll learn more about it when you get to algorithms class and actually do more fancy things. But here are some other examples that I have. Basically, I just want to do one for each case so you can see that. So, yep, we got 25 minutes to do a couple of these. We'll see if we get through at least one per case. I think this one's okay, no, yeah, this is good. So we have T of n is equal to 8t. And you know, if you want to study for the test and review the other method, you might want to try it on this using the other method. And then, you know, I'll do the Master Theorem right now, but, you know, you can do it the other method because you'll know what the answer kind of is. So it'll be good practice. But you already know what the answer should be, so you know if you do it right, okay? All right, so, you know, since it's the first one, let's just bring this down so it's easier to see. But hopefully this is obvious at this point, how we're extracting the A and the B. The D is the one that might be not so obvious sometimes, but the A and B should be very obvious. But remember though, there is this rule, you know, and I'm not going to try to trick you on a test or anything, but I might forget on what I do and not make it workable. But like, you have to make sure that it follows that A is greater than 0, B is greater than 1, and D is greater than or equal to 0, right? If it doesn't follow that, then at least you're screwed with this version of the Master Theorem. Okay? So remembering that, then we say that A here is going to be equal to 8, and B is going to be equal to 2, and here D is going to be equal to 2, okay? Again, you're only really caring about the exponent. FFN, if we looked at the FFN version of this, that is actually, yes, equal to 100, n squared and whatnot, but here, we're only looking at that exponent. Again, we ignore the 100 value. We don't really care about it. Which is, by the way, why the Master Theorem only gets you that n log n kind of thing and not the 4n plus 4n log n, because of that. In fact, you might be tempted to say, oh, there's a 4 there, so I can just throw it in the answer. But you have to be careful about that. I don't think that will always work. Just transferring that constant over to the solution, okay? So, yeah, be careful about that. It works in that case if I did it, but I don't think that's a generalization. Okay? So anyways, once you got that, then you can bring in this thing here. So let's just bring it in again. Because, last time I saw this was a year ago when I was teaching this class. Oh, nice memes. So I don't remember this myself. Maybe after today it'll be refreshed, but there's no reason to remember it when I have a piece of paper that has it for me. I have more important things to remember. So, but hey, I'm not the one taking this class. So for you, it might be beneficial to remember because it might make your tests faster. Okay. I don't know if I can get rid of the purple. Let's try. Yeah. Okay, that worked. Okay. So. Okay, so we got to plug in what the log b of a is. So that is log 2 of 8, which is equal to 3. So what we essentially have is a 3 versus a 2. And in this case, 3 is greater than 2. So which case is that? We have d something log BA, and we figure out that that's 3 and 2. You're right. Yeah, I flipped them. Good catch on that. So this should be 2, 3. So case 3. Very good. Well done. So yes, indeed, this is going to be a case 3 example. Okay, so now that we know it's case 3, then we know the solution is literally going to be n, and then we have this log b of a. And we know what log b of a is because we actually computed it earlier. So that's just 3. So then this becomes n cubed. And there you go. That's your solution. This is wrong. I put case 1 in here for some reason. I put case 1. I don't know, but it's okay. Oh, I do have the long solution for this if you want. So I'm gonna write it here, and then you can go at home and do it the other way, the 1 hour way, and then verify. But I believe if you do it that way, which I guess I did at some point, or I got on the internet, I don't remember. Assuming, because I didn't give a base case, the T of 1 is equal to 1, and I think that's what you get. So you get 1001 n cubed minus 1000 n squared, which of course, again, you don't care about this term, so you really only care about that. So try it at home. Try doing this one using the build and expand method and see if you get this answer. And if you do, then you know that you remember that method. But of course, you also know how to do this quickly with the Master Theorem. So, good. Okay? So, yeah. All right. I should probably write a note about that. Case 3. That's weird. I don't know. It's ironic because with case 1, it actually would have worked the same. Ironically, because n cubed would have worked too. But that's just like a weird scenario. But yeah. Interesting. I don't know why. Okay, let's do another one. Nah, this one's too close. This one's like, here, you can do this one at home if you'd like. That's just too close to the one that we just did, because the only difference was 4n versus 10n. So I hope you can see how that one's just going to be the same thing. So yeah, you can try that one at home. Okay. Okay, you can do this one. I actually don't know which case this one is. Okay, I like this one actually. It's nice because you have to think a little bit. All right, so again, let's just take our little template here and bring it down with us. So let's figure out, well, it's obvious that B is 3, so that one's nice. The other two require a little bit of critical thinking. Very little, not a lot, right? I mean, what is A? Well, A should be right here, but it's nothing. And here we have that. So what can we plug in? Yeah, just 1, exactly. Because, like, again, if you need to make up a number, you can make up a 1 and multiply it times something, and it's the same value. So yeah, it's just a 1 there. And then for D, it's going to be indeed a 0 because, again, it's that imaginary n to the 0, which is again equal to 1. So, you know, you just have to kind of remember those basic math sort of conversions, and then you get those 3 things, right? Now, again, don't forget, I mean, I am skipping that, but you know, you need to make sure that they follow the A greater than 0, B greater than 1, and D greater than or equal to 0 rules, which in this case they do, because I left a lot of space, because we got 1, 3, and 0, okay? So yeah, let's just go ahead and plug in that log BA component and see what that is equal to. Well, ooh, that's nasty. Okay, this is not going to be as clean, but we have 3, 1. So what is that going to be equal to? Well, actually, oh, wait a second. Why did I put 2 there? Made a mistake. Hold on. You guys had it right, but I made a mistake. The whole point of me putting this problem was to show you this trick, and I actually got fooled myself. B is not obviously 3. So Voda and 64 had it right. It actually turns out that it's 3/2. Right? Because we need to convert this at the bottom, but we also need to get rid of the 2 at the top. So if you remember, you know, if you want to put a number that's in the numerator into the denominator, you just divide it by that number. So it becomes 3 divided by 2, right? So your fractions from like 6th grade or whatever, if you have something of this format, doesn't matter what is here, doesn't matter what is here. If you want to bring this down, you have to divide both sides by half, right? So you have to divide it by 2. And then this becomes divided by 2, which just becomes 1, right? And what is currently x? Well, x happens to be a 3 in this case. So that's how we get 3/2, okay? So, very good. Thank you for that. I was like, there has to be a trick to this. Okay, so, and also I didn't like the fact that the logarithm, I mean, the logarithm just became nasty now, but that's okay. So we need to do log 3/2 of 1. Well, you know, in any scenario, I would not be looking forward to having fractions in my logarithm. But in this scenario, you know, this is okay because it's just a 1, right? So it's not a problem. because any number to a power of 0 is 1 indeed. So yeah, that's just equal to 0. So, you know, if you have a really nasty log here, I feel bad for you. However, yes, when we do just have a 1 here, then it doesn't matter what's here. Any number. In fact, I'm pretty sure that's one of the properties I said. The log to whatever is here, it doesn't matter. You know, if that is equal to 1, then this is just going to be equal to 0. So, yep, okay. So, nastiness avoided. And then we just got to compare D and this. But in this case, literally, they're both equal, right? 0 and 0. So, we should basically be looking at a case 2 again. Trying to copy it. There we go. Okay, so they're equal, and so we want this. Whoa, that's weird. How the colors change. Look at that. That's cool. All right. N to the D log n, and D is equal to 0. So this just becomes n to the 0. N to the 0 is what we just talked about for a few minutes. It's just 1. So this just becomes O, or theta actually, of log n. Okay? So that is going to be the solution to this. I was like, where's the rest of the stuff? This is on the next page. Yep. So, yeah. Okay. So that's actually a pretty good one. You know, that's kind of hardcore a little bit. You know, try to do that one with the build and expand method. It might get a little fancy and scary. So definitely try that at home. Yep, you have tons of examples that you can try if you want. Okay, so we haven't done a case 1. I don't have actually, because the other example was flipped. It's actually case 3. Let me just come up with a case 1 really fast. Okay, so let's just leave that here. Oh, come on, I did something just there. Oh, there we go. Let me just come up with an example that is case 1. So we could do something like T of n is equal to 2t of n divided by 2 plus 4n to the 5th power. Okay? I think that'll work just fine. Let me copy paste. Here, we'll just do it here since there's space. Okay, so if we do that, then our A becomes 2, our B becomes 2. I picked those numbers because I wanted an easy log. Like when we do the log BA, which is just going to be equal to 1. And then the D is equal to 5, right? So now we have a scenario where 5 is definitely greater than 1. So that's going to be case 1, okay? Because 5 is greater than 1, and so this becomes n to the 5th power, okay? And I hope that, like, from a conceptual point of view, that makes sense. If you think about this recurrence relation, every step of the way, which is logarithmic because it goes in halves each time, it's adding a n to the 5th. So probably the final answer to this is like n to the 5th times like log n, probably. But the log n is irrelevant. The n to the 5th is just such a big number that it just takes over. And that's why this is the time complexity. No, technically this is theta. That's, you know, you have to read into the Master Theorem to understand why. But like, yeah. Let's just hand wave that part. But I know what you're saying. It should be big O. And like, if you put big O there, I'm not gonna deduct points because You know, I can see where you're coming off of that. Because like, if we did the other way, then yeah, it's big O. But it happens that it also happens to just be theta based on how they structure the Master Theorem. Again, I don't want to go too in depth into that. So we'll just hand wave that part and, you know, wait till you take 477 and they explain that better. Okay. I have a comment here about showing you indivisible ones from the Wikipedia that I wrote to myself. So here, let's just show those. Why not? Okay, that did not work. Stuff is very messed up. Oh no, it's because I know what it is. I messed around with my monitors. So now, okay, for now, I'll just bring it over there. That's just, this is toxic. Yeah, it's all, ignore the fact that it's like crushed and whatnot. It's, yeah, I did some monitor configurations, and now it's like in a completely different monitor. But okay, I'll fix that for the 202 class. I just don't want to do it right now. It's too much work. Okay, so if we look at that, okay, I'm just literally gonna like go over here now. So yeah, I'll be around. If we see this case, we see that A is equal to 8, right? Oh, actually, here I can just look at it here. So I'm still looking at you guys like that. Okay, so we can see in this case that A is equal to 8, right? And B is equal to 2. And then we have n squared. Wait, but that's here. No, that's not a. That's just a generic case. Here, this one's better. The indivisible ones. Yeah, I noticed that as I was looking at it right now. That's okay though. Just D or C, whatever. I frankly don't know where I got the D from. Probably Dr. Wall uses D, and like at some point I got it from him, or some other website. Doesn't matter. Use whichever one you feel comfortable with. Okay, so gosh, that looks that's weird because it crushed. Okay, so you can see when I think of C, I'm thinking like that constant from the certificate. So yeah, just use whatever you want. It's fine. Just make sure if you use a variable, define which one you're using. Because if you're not using the A and B and D ones that I'm using, you know, I may not know what you're talking about. So make sure you define it by writing the formula. The A to the T, you know, of n divided by B. If you're going to use X, Y, Z, then say something like T of n is equal to X T of n divided by Y plus theta n to the power of Z. And if you put that on the top, then I know what variable you're using. So if that way I know which letter you're using, okay? You should technically do that all the time. But I guess if you're using A, B, and D, then I just make that assumption because I know. But in theory, you should always use that to explain to people what your variables mean, right? So, yeah. Okay. It looks okay on this hand. Yeah, to me it looks crushed. Okay, so this one's 2 to the n, t n divided by 2 n to the n. Ooh, yeah, that's nasty. So the B is okay because that's just 2. The D is equal to n, which, or D or C, whatever, which isn't ideal. But the bigger problem is the 2 at the beginning. So the A. The A is equal to 2 to the n. Whenever you're dealing with these n's, you know, these are supposed to be constants. A, B, and D are all supposed to be actual numbers, and they're static. It can't be changing, so they're constant. So they can't have a variable like n involved. So it breaks it because of both of those, okay? The second one, 2 to the t, n divided by 2 plus n log n. The 2, so the A and the B are fine, it's just 2 and 2. The problem here is that D or C or whatever, because when you convert this into a format that is n to the power of something, you know, you end up with that n log b, like you would end up with a like Like you can multiply, you could do log n on both ends. You know, you could say log n here and log n there, so you would end up with like a, no, like you could flip it around by multiplying with a fraction, but ultimately, as it says there, like it just becomes an like that. You can't get a nice d out of that. You know, you still end up with something related to like an exponent that has an n in it. Okay, and what they mean by non-polynomial there is what I was talking about like a long time ago, where I said like n squared, n cubed, n to the fourth. Those are all polynomial. But when you get to exponential stuff like 2 to the n, that's exponential, and that's really slow and bad. So the Master Theorem is meant for only polynomial stuff. So that's what I mean with non-polynomial there, okay? But I mean, it should be obvious that like when you can't find like a nice clean d value, that something's wrong. The third one is you know this is the one where like you see this, you might be like, oh, b is 2, d is 1, and a is 0.5. They're all numbers, and you plug them in, and you can actually compute that. You can compute like log of 2 of 0.5 or something, and then compare it to your d and see, okay, 1 is greater than that value or whatever. The problem with doing all of this is that you got to remember that there's this constraints that a has to be greater than 1, right? And d has to be, or it's a 1, a has to be greater than 1, and then d has to be greater than 1 as well. So I forgot if it's greater than 1 or 0. Hold on, let me triple check that. I guess technically it would be 0 for a. Let me just check it. A has to be greater than 0, right? So a has to be greater than 0, b greater than 1, and d greater than or equal to 0. And so the a has the a is actually, well, why does it say there a is less than 1? So a is less than 1, cannot have less than 1, so problem. So maybe it has to be greater than 1, and I put it as 0, but it should have been 1. Probably. So maybe maybe they all have to be greater than 1, and I just had it off there. I'll have to check on that. But yeah, so that apparently wouldn't work because of that. Okay, because you have to be greater than 1. Under the next one is again with the d, because you can't have you have this log n next to this n, and you can only have one of the terms, and it has to be just an n, so it complains about that. It doesn't work out. And then the third one is it's kind of weird, and let's not talk about, well, not the one, the final one is kind of weird about that, so let's just move on to that one. Yeah, it's like traveling in time. Yep. Okay. So yeah. Okay. So anyways, these are some weird ones. I'm not going to try to trick you on tests and things like that. I'm just making you aware of this, because when you're doing your assignment, if you try to use a Master Theorem on something you shouldn't, it's going to give you completely wrong time complexity for your problem. So it's good to check that. Again, unless you're doing some nasty code where you have a situation like that, maybe, if you get into a situation where you can't use a Master Theorem because your code is so messy, you should reflect on maybe fixing your code at that point, instead of trying to analyze some super complicated recurrence relation. You should be like, maybe I shouldn't be using recursion on this, or like maybe I should use cleaner recursion, because most code will be clean enough that you can use the Master Theorem on, at least for this class. But you never know. Like the CS:GO assignment or something might be really fancy, but nah. So anyways, that's it. That is all the time that we have for recurrence relations. Starting next class, what are we going to be doing? Let's see. We're going to talk about linked lists and stacks and queues and arrays a little bit, okay? Most of that is going to be hopefully reviewed from 202, but we're going to be analyzing the time complexity of things now. Like, we're going to do a deeper analysis. We're gonna, more than like me showing you like, hey, this is a linked list. This is how you link things together. Like, no. I expect you to know what a linked list is. This is more of like, okay, what is the time complexity of inserting something onto the linked list, and compare that to the arrays and whatnot. It's when we're going to get more into the analyticals of these things, okay? So that'll be on Wednesday. Until then, get your assignments done, and if you have nothing to do, then you can start on the final project that's already available too. So, yep. thank you all for coming. I'm going to go and fix my monitor issue before the next class, because I do have to share my screen for that. All right? So thank you all, and I'll see you on Wednesday, all right? Take care, everybody. Bye.